Hello everyone, welcome back to my channel. In this lecture, we are going to learn another important category of the 8085 microprocessor instruction set, that is arithmetic instructions. As the name suggests, arithmetic instructions are used to perform mathematical operation on data stored in the microprocessor. These operations include the addition, subtraction, increment, decrement, and decimal adjustment. Whenever microprocessor needs to perform a calculation, it uses arithmetic instruction. Most of these operations are carried out using the accumulator, which is represented by register A. However, some instructions also operate on register pairs, such as HL register pair. Now let's see what topics we are going to cover in this chapter. Now one important question is, why are arithmetic instructions so important? These instructions are the foundation of almost every program. They are used to perform calculation, update values, process data, implement counters and loops, and support decision making in embedded system. Another important thing to remember is that arithmetic operations are also affect the status flags of 8085 microprocessor. These flags are sign flag, zero flag, auxiliary carry flag, parity flag, and carry flag. These flags tells us important information about the result of an operation, such as whether the result is zero, negative, even parity, or if a carry or a borrow has occurred. Throughout this chapter, we will also discuss which flags are affected by each instruction, because it is a very important topic for your examination. So with the basic introduction complete, let's begin with the addition instruction, starting with the very first instruction, add. Remember, add stands for add register or memory to accumulator. This instruction adds the content of a register or a memory location to the accumulator, and the result is always stored back to the accumulator. One important thing to remember is that the destination is always the accumulator. The source can be either a register or a memory location. If the operand is M, it represents the memory location whose address is stored in the HL register pair. Also, after performing the addition, all the flags, that is 0, sign, auxiliary carry, parity, and carry, are updated according to the result. If we look at the representation, we have the accumulator A plus the register or memory represented by R or M, and the result is stored back to the accumulator. Let's understand this with an example. Suppose we execute this instruction, add B. Here accumulator A contains 25H and B contains 15H. The result became 3AH. This value is stored back in the accumulator. Therefore, accumulator A is equals to 3AH. Notice the register B still contains 15H. Only accumulator changes. Now let's move to the second instruction, which is ADI. ADI stands for add immediate to the accumulator. The word immediate means the data is directly written inside the instruction itself. Unlike add, where the data comes from a register or memory, here the processor add an 8-bit immediate value directly to the accumulator. Again, the result is stored in the accumulator and all the flags are updated. If we observe the representation, accumulator A plus 8-bit immediate data give the result stored in accumulator. Let's solve the example. Instruction is ADI 87H. Suppose the accumulator initially contains 20H. The immediate data is 87H. Now perform the addition. Therefore, accumulator now stores A7H. Again, the immediate value is not stored anywhere. It is simply used for the calculation. Now let's study the third instruction, which is ADC. ADC stands for add register or memory with carry. This instruction is almost same with add, but one extra thing is involved, that is carry flag. So instead of adding only the accumulator and the operand, the processor also the value of the carry flag. If the carry flag is 1, it contributes an additional 1 to the result. If it is 0, then it behaves exactly like the add instruction. If you see accumulator A plus register or memory plus carry flag give the result, which is stored back into the accumulator. Let's understand with this example. Suppose we execute ADC-E. Initially accumulator is 12H, register E is 34H, and carry flag CY is equals to 1. Now if the processor performs the addition, therefore accumulator became 47H. The addition 01H comes because the carry flag already set. Before moving to the next slide, let's quickly revise this important point. Add adds data from a register or memory to the accumulator. ADI adds the immediate 8-bit value to the accumulator. ADC adds the register or memory along the carry flag. All these three instructions, the result is always stored to the accumulator. If the operand is M, it refers to the memory location addressed by the HL register pair. Finally, all the status flags, sign Z, auxiliary carry, parity, and carry updated after the operation. Now that we have understood all these three instructions, let's move on the next set of arithmetic instruction. Now the next instruction is ACI. ACI stands for add immediate with carry. In this instruction, the processor adds three values: the content of accumulator, and 8-bit immediate data, and the carry flag. The result is stored in the accumulator as usual, and all the carry flags are updated. Let's understand with the example. ACI 45H. The accumulator contains 28, suppose, and the carry flag is already set. So after the calculation, the result became 66H. This value is stored back to the accumulator. Up next, DAD instruction. DAD stands for double addition. Add register pair to HL register. Unlike the previous instruction, this is a 16-bit addition. Instead of using the accumulator, it adds a register pair to the HL register pair. The result is stored in the HL register itself. One important point is only the carry flag is affected. None of the other flags change. Now suppose HL register contains 2500H and BC contains 1234H. The instruction is DAD B. After performing the addition, HL becomes 3734H. If the addition exceeds 16-bit, the only carry flag becomes 1. Otherwise, carry remains 0. Up next, we have SUB, subtract register or memory. It subtracts the contents of a register or the memory location pointed by HL from the accumulator. The result is stored back to the accumulator and all the flags are updated. Let's take the instruction SUB-C. Suppose the accumulator contains 45H and register C contains 12H. After the perform of the subtraction, the accumulator became 33H. Similarly, if we write SUB-M, the processor subtract the value stored in the memory location addressed by the HL register pair. Next instruction is ACY. ACY stands for subtract immediate from accumulator. Here, instead of taking the operand from the register, the processor subtracts the 8-bit immediate value directly from the accumulator. Again, the result is stored in the accumulator and all the flags are updated. Let's see the example. Instruction ACY 98. Suppose accumulator contains B5H. After the subtraction, we have 25H. Now accumulator contains 25H. Up next, we have SBI. SBI stands for subtract immediate with borrow. Similar to SUI, there is one extra value, the borrow, which is actually represented by the carry flag. So the processor subtract the immediate data and also subtract the carry flag. Now understand with an example. Instruction SBI 25H. Suppose accumulator contains 50H, the immediate data is 25H and the carry flag is set. Now the operation performed, therefore the accumulator became 2AH. So remember, SBI is simply SUI plus borrow. Let's quickly revise what we learned. ACI adds immediate data along with the carry flag that performs a 16-bit addition between HL and another register pair. Subtract a register or a memory from the accumulator. ACOI subtract an immediate data. HBS subtract immediate data along the carry flag or the borrow flag. Except that all the instruction updated all the flag. Only that affect only the carry flag. Up next we have SBB. SBB stands for subtract register or memory with borrow. This instruction is very similar to SUB instruction but with one important difference. Along with subtracting the register or memory value, it also subtracts the borrow, which is represented by the carry flag in 8085 microprocessor. The processor performs three operations: accumulator minus operand minus carry flag, and the result stored back to the accumulator and all the flags are updated. Let's see the example. The instruction is SBBD. Suppose accumulator A is 50H, register D is 20H and carry is 1. After the calculation, the final result is 2FH. Therefore, accumulator is equals to 2FH. Always remember SBB is equals to sub instruction plus borrow. Next, we have INR, increment register or memory by 1. This instruction increases the value of register or a memory location by 1. The updated value is stored back in the same register or memory location. If the operand is M, it means memory location pointed by the HL register pair. One important point to remember is that the carry flag is not affected by INR instruction. Now let's just understand with example. The instruction is INR B. Suppose register B contains 3FH. So the processor adds 1, therefore B becomes 40H. One quick revision: ACUI subtract an 8-bit immediate value from the accumulator. SBB subtract a register or memory value along with the borrow or carry flag. SBI subtracts an immediate value along with the borrow. INR increments the register or memory location by 1. Let's move on to the next arithmetic instruction. INX. INX stands for incremented register pair by 1. I have told you that X means the 16-bit register pair. This register pair can be BC, DE, HL or even the step pointer. The updated value stored back into the same register pair. One important point to remember is INX doesn't affect any flag. Let's understand with example. The instruction is INX H. Here H contains 25H, L contains 0FH, so together HL register pair contains 250FH. After the addition of 0001, the HL register became 2510H. Up next we have DCR instruction. DCR stands for decrement register or memory by 1. This instruction decreases the value of a register or a memory location by 1. If the operand is M, the memory location addressed by HL register pair is decremented and the result is stored back in the same location. One important point is that all flags are updated except the carry flag. Let's see the first example. Instruction DCRC. Suppose the register C contains 40H. Now we subtract 1, therefore register C becomes 3FH. Now see the next instruction, that is DCRM. Suppose the memory location pointed by HL contains 2AH. Now decrement it by 1. So now the memory location now store 29H. Again all flags are updated except the carry flag. Up next we have DCX. It stands for decremented register pair by 1. Unlike INX, it can be used with DC, DE, HL or SP. Again this result is stored back in the same register pair. Unlike INX, no flags are affected. Let's understand with the example. Instruction DCXH. Suppose HL contains 3000H. Now subtract 1 and the result becomes to FFFH. Since register pen operation, none of the status facts change. Now let's study the final arithmetic instruction, which is DAA. DAA stands for Decimal Adjust Accumulator. This instruction is little different from all the previous instruction. It is used to convert the binary result stored in the accumulator into a valid BCD number. The instruction is commonly used in applications like digital clock, calculator, digital counter, and 7-segment display, where decimal number needs to be displayed correctly. Now let's understand how DAA works. There are two rules. Rule 1. If the lower 4-bit, also called lower nibble, are greater than 9, or if the auxiliary carry flag is set, then the processor adds 06H to the accumulator. Rule 2. After that, if the 4 upper bit or the upper nibble became greater than 9, or if the carry flag is already set, then the processor adds 60H. This converts a binary value into a valid BCD number. Example, suppose accumulator contains 9DH and auxiliary flag is 1 and carry flag is 0. Step 1. Since the lower nibble is D and 13 in decimal, which is greater than 9, now auxiliary carry flag is also set, so we add 06H. So 9D plus 06 result A3H. Now the accumulator contains A3H. Step 2. Now observe the upper nibble. There is A, which is 10 in decimal, and that is also greater than 9. Now we add 60H, A3 plus 60H, which is 103H. Since this is a 8-bit accumulator and the lower 8 bits are stored, so the accumulator finally contains 03H and the carry flag became 1. Therefore, the final BCD result is 03. With the carry equal to 1, unlike INX and DCX, DAA also update all the status flag. Let's quickly summarize the instruction. INX decrement 16-bit register pair by 1. DCR decrement a register or memory by 1. DCX decrements a 16-bit register pair by 1. DAA converts the binary result in the accumulator into a valid BCD number. With this, we have successfully completed all the arithmetic instruction of the 8085 microprocessor. In the next lecture, we will move on to the next category of 8085 instruction set. Thank you so much for watching and supporting our content. Your like, comment and encouragement motivate us to create more educational video. If you find this lecture helpful, don't forget to like, share and subscribe to our channel. Happy learning. See you in our next video.